All of our calculations and modeling of gases using the gas laws or kinetic molecular theory is based upon gases behaving exactly as we expect, or based upon the assumptions of the kinetic molecular theory, that the particles themselves are so small, their volume doesn't matter, and that the collisions between them are completely elastic. Although that is very close to true under most circumstances, it is not 100% true. If we are at high temperature with low pressure, gases act very close to ideal. And room temperature is hot enough to be high for most gases. Atmospheric pressure is low enough to be low for most gases, which is why the kinetic molecular theory and the gas laws works very well under most conditions. In reality, there are some issues with this. It can be corrected with a more advanced version of the ideal gas law, but for our purposes, we just want to think about where the shortcomings are and why we may have some issues. So first off, the gases themselves, the particles themselves, do have volume. So when we assume that they don't, obviously that's not true. We would take just the container's volume as if that's the volume of the space between the particles. Well, the particles themselves would take a tiny bit of space, and depending whether we had a rigid container or something flexible like a balloon, which may be easier to think about, that would throw off our calculations. In a balloon, for example, the volume of the particles themselves would add to any calculated volume and slightly change any calculations or predictions from the KMT and the gas laws. Maybe the more significant thing is the IMFs. Some gases or some particles exert higher and stronger IMFs on one another than others. That would cause them, when they pass by one another or collide with one another, to stick together a little bit more. In those cases, we would have some loss in kinetic energy, and therefore we would not see the exact predicted volume or pressure for our gas. The higher our temperature, the faster our particles are moving, and therefore less likely to stick together. The lower the pressure, the farther apart the particles are, or the fewer particles in a given area, and the less likely they are to stick together. So what we would want to recognize here is just those are the two shortcomings, IMFs and particle size itself. Here on this graph, which is a common way that it's shown, shows us at lower pressures here and at different temperatures how far from ideal our gas may be. This highest temperature, almost 1000 Kelvin, a gas is as close to ideal as possible. The lower our temperature goes, and at different pressures here, we start to see at high pressures really extreme issues, at low pressures different and much smaller issues. And if we zoomed in right here, we would see when we are at 10 or fewer atmospheres, we are pretty close to ideal for most gases. When we are at room temperature, our greenish line, standard temperature in terms of thermodynamics, we are pretty close to ideal. So we can understand the why, but not really worry about the circumstances in which we would be acting non-ideally.